So welcome all for today's session. My name is Mr. John Mark, a lecturer at KCE. And for today's QA session, we'll be learning about matrices. So what's matrices? Now matrice is just the arrangement of numbers which have been enclosed within a bracket. That's what we call a matrix. And then we have said that those numbers which are enclosed within the bracket, they are known as elements. And then for the order of the elements, we have two orders under the elements. We have what we call a vertical arrangement of elements, and the vertical arrangement of elements is known as the columns, while we have the horizontal arrangement of numbers, which is known as rows. So that's basically what we call a matrix. And we are saying that matrices or a matrix is just a rectangular arrangement of numbers which are enclosed within a bracket. And then we are saying that these numbers are known as the elements. So the numbers are known as elements. And then we have also said that about the order of the elements. So, for example, let me give you an example of a matrix. Assume we have A, B, C, and D. Now, that's what we call a matrix. And then under the matrix, we have the numbers. Those numbers are what we call the elements. This is what we call a matrix. Then another thing we have said that under this matrix, we have vertical arrangement of the numbers, and this vertical arrangement of numbers is what we call the column. Also, we have horizontal arrangement of numbers, and the horizontal arrangement of numbers, this is what we call a column. That's what we call a column. So that's basically what we call a matrix. A matrix has elements and then it has its own orders. We have we are saying that the horizontal arrangement of numbers, this is what we call a row. What's not a column, it's a row. Good. So that's what we call a matrix. And then under the matrix, we usually have what we call the diagonals. So for example, assuming I give you a matrix like this, A, B, C, D. Assuming I give you a matrix like that. So now, under this matrix, we have two diagonals. We have this diagonal, and this is what we call major diagonal. Then, we still have another diagonal. We have this. Now, this is what we call a minor diagonal. And what are the purposes of getting or determining the diagonals? Both the major and the minor diagonal. Diagonals help us in determining what we call a determinant. So what's a determinant? So to get the determinant, we use the diagonals. And in this case, you take the major diagonal, you deduct minor diagonal. So for example, in this matrix, assuming I want to get the determinant, I'll take the major diagonal. So in this case, we have A and D. So you'll take A, you multiply by D, then you deduct minor diagonal. And for the minor diagonal, we have elements C and B. So you take C, you multiply by B. That's how you get the determinant. Later, I come to show you how do we apply determinant. A determinant is mostly applicable when you are getting an inverse of a matrix. Good. So now I want us to look what are the various types of matrices. We look at types of matrices. Let's look at types of matrices applied in business. And number one, we have what we call a nil or a zero matrix. Now, what's a nil or a zero matrix? A zero matrix is a matrix with no element. This one is a matrix with no element, and it's denoted by that. Now that's what we call a nil or a zero matrix. Another matrix we have, number 2, we have what we call a single tone, or what we call a scalar matrix. And what's a scalar matrix? The singleton or scalar matrix is a matrix with only one element. Is a matrix with only one element. And it's denoted by this. So assuming we have a matrix like that, and we only have one element. Now this is what we call a singleton or a scalar matrix. Number 3, we have what we call a square matrix. And what's a square matrix? Now, a square matrix is a matrix with equal number of rows and columns. Yeah, has equal number of rows and columns. For example, we may have a matrix of a 2 by 2 matrix, a 3 by 3 matrix, a 4 by 4 matrix, etc. So in this case, we are saying that is a square matrix is a matrix with equal number of rows and columns. And in this case, this is how we get the order. So that means we have 2 rows, 2 columns, 3 rows, 3 columns. Now, under this, the arrangement of the matrix is denoted by what we call an order. So for example, in this matrix, under this matrix, so how do we determine the order of this matrix? This is how we determine the order. First of all, we use the rule of 7. The rule of 7, always you start with the number of rows and then you get the column. You draw a 7. So always you start the number of rows. So in this case, we have 1, 2. So that means we have 2 rows and then columns 1, 2. So that means that matrix is an order of a 2 by 2 matrix. Has equal number of rows, equal number of columns. So that's what we call a square matrix. Number 3 or number 4, we have what we call a column vector matrix. So what's a column vector matrix? Now, a column vector matrix is a matrix with only one column but more than one rows. I repeat again. We are saying that a column vector is a column vector matrix is a matrix having only one column but more than one rows. So for example, we have A, B, C, assuming we have that matrix. So in this case, we only have one column, but we have more than one rows. So you're saying that in this case, you only have one column, but more than one rows. So that's what we call a column vector matrix. So let's look at another type of matrix. We look at another type of matrix. So number 5, we have what we call a row column. Sorry, not a row vector matrix. Row vector matrix. Now, a row vector matrix is a matrix with only one row but more than one row but more than one column. So, for example, we may have A, B, C. Now, that's what we call a row vector matrix. It has only one row but has more than one column. So that's what we call a row vector matrix. Number 6, we may have what we call identity matrix. What's an identity matrix? Now, an identity matrix is a matrix whose major diagonal elements are 1s and all other elements are 0s. I repeat again, identity matrix is a matrix whose major diagonal elements are 1s and all other elements are 0. So for example, assuming you have a 2 by 2 matrix, you may have 1, 0, 0, 1. That's what we call an identity matrix, in which the major diagonal elements are 1, but all other elements are 0s. Or, assuming it's a 3 by 3 matrix, so you may have 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's another identity matrix. So if you look at the major diagonal elements, they are ones, and all other elements are 0. So another type of matrix, number 7, we have what we call a diagonal matrix. Now, a diagonal matrix is a matrix in which the elements of the diagonal are shown without the elements above them. So, for example, we may have A, B, C, D, E, F. That's an example of a major diagonal, a diagonal matrix. So you see in this case, the major diagonal elements are shown without the elements below them. Or we may have A, B, C, D, E, F. We may have a matrix like that. You see, also in this case, they forms a diagonal. In this diagonal, they are shown without the members above them. It can either be below or above them. And lastly, number 8, we have what we call transposed matrix. Transposed matrix. And what's a transposed matrix? Now, a transposed matrix is a matrix whose the rows and the column have been interchanged. So the rows becomes the column and the columns becomes the rows. So a transposed matrix is a matrix whose column and the rows have been interchanged. So for example, assuming you have A, B, C, D as the matrix. So now let's transpose that. If you transpose that, that means it will be the first row becomes the first column of the other matrix. So here we have A, B, and then the second row, when transposed, becomes the second column. So you'll have C, D. Yeah, that's what we call a transposed. So what we have done, we have interchanged the rows and the column. You see in this case, the first row is the first column of the second matrix. And then the second one is the second column. Also, the first column, in this case, it becomes the first row under that one. So those are the various type of matrices applied in business. We have said that we have a nil, a singleton, we have a row vector, the row vector matrices, and also we have the column vector matrices, we have identity matrix, we have transposed, and we have diagonal matrices. So those are various types of matrices. So we go to another part. So now I want us to look at what we call operations of matrices. What are some of the operations of matrices? 1, we may have addition. Number 2, subtraction. Number 3, we may have multiplication. And number 4, division, or what we call inverse. So those are the 4 applications of matrices. And number 1, let's start with addition. Addition of matrices. Yeah, addition of matrices. How does the additional in a matrices work? So in this case, it's just a normal, a 1-by-1 matrix. But in this case, what matters mostly is the order of a matrix. So, and for the order of matrix, sometimes it has to be compatible, others not a must to have to be compatible. So, for example, if you are given a matrix, we are doing addition of matrix, you are given 2, 4, 6, 9, you add 9, 3, 2, 1. Like that. So, what's the answer there? So, in this case, it's a 2-by-2. So, you'll do 2, you add 9. So, 2 plus 9, you get 11. 4, you add 3, you get 7. 6, you add 2, you get 8. 9, you add 1, you get 10. As simple as that. So no additional concept is required there. So now let's do another illustration. Assuming now you are given a 3-by-3 matrix. For example, you are given 2, 4, 3, 9, 6, 4. You add, assuming now you are given, you add 4, 3, 2, 6, 9, 3. Assuming you are given a matrix like that. Is it making economic sense? So in this case, we can say it's spurious. Because in this case, you cannot take 2 plus 4 and then 4 plus 3. What about the 2? So in this case, for example, the order of this, it's 1, 2, 3. So it's 3. Then you count the number of rows. 2, like that. And then here we have 1, 2. 1, 2, 3. So it's a 3 by 2 and a 2 by 3. So in that case, they cannot work together. Good. So for it to work, it must be a square matrix. That's not necessarily a square matrix. They should be somehow compatible. So that's how addition of matrices works. What about subtraction? What about subtraction of matrices? What about subtraction? Now, subtraction and addition, they are almost the same. They are almost the same. So number 2, we are looking at subtraction of matrices. Assuming you are given 4, 9, 6, 3, a matrix like that, you minus 2, 7, 9, 4. So what do you get there? So in this case, you do the way you have done the first one. So you take 4, you deduct 2, and you get 2. 9, you deduct 7, you also get 2. 6, you deduct 9, you get negative 3. And then 3, you minus 4, and you get negative 1. It's as simple as that. Simple as that. So that's the addition and subtraction of matrices. So now let's go to the most applicable and the most important operation of the matrices under this. Multiplication and division. Those are the most important under the operations of matrices. So I want us to start with multiplication. Multiplication of matrices. Multiplication of matrices. Now, a matrices can only be multiplied if the matrices are compatible. Let me repeat again, that we can only multiply a matrix if the matrices are compatible. And if they are applied for commercial purposes, they must be both compatible and feasible. Feasible means that they are making economical sense. What do we mean by compatibility? So we are saying that it must be compatible. For example, assuming you're having a matrix of a 2 by 2, and then you are multiplying by another matrix of a 2 by 2. This is how we look at the compatibility. Compatibility, you look at the number of columns of the first matrix, and number of rows of the second matrix. So this is what I mean. This is what you do. We have said that you look at the number of columns in the first matrix, and this is the number of columns. We have 2 there. And then for the second matrix, you look at the number of rows, and this will present the number of rows. So in this case, we are looking 2 and 2. If this is 2 and the other one is 2, that's when you say that that matrix is compatible. Is compatible and can only be multiplied when they are compatible. Now, assuming you are given a 2 by 3 matrix, you multiply by another 2 by 3 matrix. A 2 by 3 matrix and a 2 by 3 matrix. You ask yourself, is it compatible? So, we shall say this is what you look. You look at 3, and this one you look at 2. So here we have 3, we have 2. So that means in this case, it's not compatible. What if you have a 2 by 4 and another 2 by 4? 2 by 4, 2 by 4 matrix. Is it compatible? So we are looking at 4 and 2. Still that one is not compatible. When it's not compatible, that means you cannot solve it. Now, let me try to interchange in this case. What if you take a 2 by 4 and then a 4 by 2 matrix? A 2 by 4 matrix, you multiply by a 4 by 2 matrix. So in this case, we are looking at 4 and 4. So in this case, we can say, you see, if we have 4 and we have 4 there, so that means our matrix is compatible. And that means they can be multiplied. Good. So one point you need to know that for the matrices to be multiplied, they must be compatible. And then if they are applied for commercial purposes, it must be both compatible and feasible. Good. So what are the steps forward? Let's look at the steps forward. Steps forward. And step number 1, you compute determinant. Compute the determinant. Then step number 2, you reciprocate the determinant. Reciprocate determinant. Then step number 3, for the major diagonal elements, comma, you need to interchange. You interchange. And lastly, for minor diagonal element, you change the sign. Change the sign. As simple as that. So you're saying that steps forward number 1, you determine the determinant. And we said, how do you get the determinant? Determinant, you take the major diagonal element minus minor diagonal element. Then step number 2, after you get determinant, you reciprocate the determinant. After you reciprocate the determinant, for the major diagonal element, you interchange. But for the minor diagonal element, you change the sign. So let's do an illustration on that. I want us to do an illustration. So I want us to do an illustration. But now, kindly, for the steps I have given, you, that's for the division. So I have gone one step ahead. So kindly, first of all, you know about the steps. So that one will cover the steps when it comes to getting the inverse. So for the multiplication, it's all about being compatible. So first of all, ignore the steps that I have given you. Those steps will belong when you're dealing with division. So we go back to the multiplication. Only multiply the matrices if they are compatible. And this is how we do it. So we do an illustration. This is the first illustration. Assuming you are given this matrix, and you are supposed to multiply by that matrix. How do we multiply? This is what you do. We say that you use the rule of 7. 7. Always you start with the rows before you go to the columns. So that means, for example, in this case, I'll do this. First row, first column. First row, first column. So this is what I'll do. 4 you multiply by 1. So I'll take 4 you multiply by 1. You add 3 you multiply by 4. 3 you multiply by 4. So that's first row, first column. Then first row, second column. First row, second column. So that means I'll take 4 you multiply by 3. 4 you multiply by 3. Then you add 3 you multiply by 2. 3 you multiply by 2. Then we go back here. Now you take the second row, first column. Second row, first column. So that means you take 2 you multiply by 1 plus 1 you multiply by 4. So you'll take 2 you multiply by 1. You add 1 you multiply by 4. And then second row, second column. Second row, second column. So that means you take 2 you multiply by 3. So it's a 2 by 3. Then you add 1 by 2. 1 by 2. So now we simplify that. So that's 4. You add 12. So 4 you add 12. You'll get 16. Then we have 12. 4 times 3 is 12. Plus 6. That one you get 18. 2 times 1 is 2. Plus 1 times 4 is 4. So it's 4 plus 2, you get 6. And then here we have 2 times 3, which is 6. 6 you add 1 times 2, which is 2. So 6 you add 2, you'll get 8. As simple as that. So if you multiply this matrix and that one, the product should be 16, 18, 6, and 8. So now let's do another illustration. Illustration 2. Illustration 2. Assume now you are given a 4, 3, 2, 9, 1, 2, 3, 0. And you have to multiply, eh? So assuming you have that, so you have said that first row, first column, first row, first column. This is what you do, eh? You take 4 times 1, which is 4, plus 3 times 3. So you're saying that 4 times 1, you will get 4, plus 3 times 3, you get 9. First row, second column. So that means you take 4, you multiply by 2, you get 8. You add 3, you multiply by 0, and you get a 0. Then we go to the second column. Eh? Second row, first column. Second row, first column. So it will be 2, you multiply by 1, you get 2. You add 9, you multiply by 3. And 9 you multiply by 3, you have is 27. And lastly, second row, second column. Second row, second column. So you'll take 2 times 2, and you'll get 4. You add 9 times 0. 9 times 0 is 0. So you are taking 2, you multiply by 2. 9, you multiply by 0 to get that. So, and then, so 9 plus 4, you get 13. 8 plus 0, you get 8, sorry. Then 2 plus 27, you get 29. And then 4 plus 0, you get 4. We have gotten the product because they were compatible. For example, let me take you back to this, to the first one. To the first one. The first problem was, the first matrix, this was a 2 by 2. We have said that how to determine the order. You count the number of rows, 1, 2, and then you count the number of columns, 1, 2. So it's a 2 by 2. And we multiply by, also this one is a 2 by 2. So we look at this and that. So that means it's compatible. The second matrix, the same. So I want to give you another illustration. Eh? What if now you do this? You are given this matrix. You are given 2, 4, 3, 9, 1, 2. You multiply by 6, 3, 4, 9, 2, 1. So step number 1, you test for the compatibility. So that means this is 1, 2, 3. So it's a 3 by 1, 2. It's a 3 by 2. Also the second one is a 3 by 2 matrix. 3 by 2. So you look at 2 and 3. So you see they are not compatible. So the solution to that, you say that it's not compatible. It's not compatible. As simple as that. So that's all about the multiplication of matrices. And you need to get this concept because it will be applicable throughout this topic of matrices. Now, lastly, for the operation of matrices, lastly, I want us now we look at how do we get division. How do we get division or inverse? Inverse of a matrix. Division or inverse of a matrix. Now, under the division or inverse, what are the steps in getting the inverse? So, steps forward. Steps forward. Now, this is where you apply the steps that I had given you earlier. That we say that number 1, you determine or you compute the determinant. Then step number 2, after you determine the determinant, you reciprocate. Reciprocate the determinant. Then step number 3, we have said that for the major diagonal element, major diagonal elements, you just interchange. You interchange. But for the minor diagonal element, you change the sign. Change the sign. Yeah, those are the steps forward when we're getting an inverse of a matrix. So let's start with the 2 by 2 matrix. How do we get an inverse of a 2 by 2 matrix? Assuming you are given a matrix like this, illustration 1, we are told that determine or compute the inverse. Compute the inverse or get the inverse of the following matrix. of the following matrix. And you are given 4, 2, 3, 1. You are given like that. If you want to get the inverse, it will be noted by this sign, like that. -1 there. So now, let's get the inverse of that. So we have said step number 1, you compute the determinant. And how do we get the determinant? This is how we get the determinant. We say that determinant, you take major diagonal element minus minor diagonal element. So for example, in this case, our major diagonal element is 4 and 3. So you'll take 4, you multiply by 3, minus minor diagonal. This is our minor diagonal. At minor diagonal, you'll take 1 times 2. 1 times 2. Like that. So here you have 12 minus 2, and you'll have 10. So that's the first step. After determining the determinant, step number 2, you compute, you get the reciprocal. How do we get the reciprocal of this? This is how you get the reciprocal. So this 10, it's more of 10 over 1. So to get the reciprocal, you just interchange. So it would be 1 over 10. So it would be 1 over 10. Then let's go to step number 3. We say that under step number 3, you interchange the major diagonals. So for example, in this case, these are major diagonal. We have 4 and 3. You just interchange them. So 3 comes there and 4 goes there. Then last step, for the minor diagonal, you change the sign. For the minor diagonal, you change the sign. For example, this is positive 2. So it will be negative 2. This is 1. It would be negative 1. As simple as that. So that's how we get an inverse over 2 by 2 matrix. So I can still show you another illustration. Let me show you another illustration still on that. If you are given 6, 4, 2, 3. You are given like that. Or assume this is still 3. And then you are given that. You have said that that's the symbol of an inverse. So let's get the inverse of that matrix. So step number 1, you get the determinant. And how do you get the determinant? You take a major diagonal element, which is 6, you multiply by 3. You deduct minor diagonal element. These are minor diagonal element. And we have 3, you multiply by 4. So that's 18 minus 12, you have 6. And then the other step, you reciprocate the determinant. So in this case, you have 1 over 6. And then, for the major diagonal element, you interchange. These are our major diagonal elements. We have that. We just interchange. So 3 goes there, and 6 goes there. And then, for the minor diagonal, these are the minor diagonal elements, you change the sign. This is 4, so it will be negative 4. This is positive 3, it will be negative 3. And that's how we get the inverse of that matrix. So that's how we get the inverse of our 2 by 2 matrix. It's as simple as that. Simple as that. So now let's how do we get an inverse of a 3 by 3 matrix? So an inverse of 3 by 3 matrix, it involves some steps, the way you have gotten for inverse of a 2 by 2 matrix. And what are those steps? Those step number 1, you have to compute what we call the minor. After you compute the minor, step number 2, you get what we call the adjoint. I've indicated the steps here. So step number 1, you get the minor. Step number 2, you compute all what we call the adjoint. Then you get the cofactor. You compute the determinant, and then you get the inverse. So those are the steps followed. You don't have to cram the format. Are the steps followed. So I'll show you how to get the minor, how to get the adjoint, to get the cofactor, and how to get the determinant, and then how to get the inverse. So now I want us to do an illustration. I want us to do this illustration here. Let's do this illustration. You are given this in matrix. It's a 3 by 3, and then we say this symbol means you are getting an inverse. So how do we get that? We have said that step number 1, you get the minor. Get the minor. And how do we get minor? So to get the minor, in this case, for example, the first one, you take first row, first column, first row, first column. Now you focus on the uncancelled number. If you take first row, first column, that means the uncancelled number we have it 6, 4, 1, 2. and then you put it like that. Then you take first row, second column. First row, second column. The untouched number you have is 2, 0. So you have 2, 0, and then 1, 2. 1, 2, like that. Then we have first row, third column. First row, third column. So the untouched number we have is 2, 0, and then 6, 4. Like that. Then we go to the second row. Second row, first column. Second row, first column. So you have the untouched number 3942. So you have 3942 like that. Second row, second column. Second row, second column. So you have 4092. So you have 4092. Then we have second row, third column. Second row, third column. So untouched number you have it's 43 and then 04. 04. Like that. And then we go to the third row. Third row, first column. Third row, first column. So the untouched number you have is that. So you have 3691 like that. Then third, second. So you have 4291. So 4291. And lastly, third row, third column. Third row, third column. So we have 4236. 4236. That is it. So that's the first step. That's the first step. Then we go to the second step. How do we get the second step? Second step, you are supposed to get the adjoint. You get the adjoint. Now, how do we compute the adjoint? So how do we compute the adjoint? This is how we compute the adjoint. To get the adjoint, you compute the determinant of each minor. And how do we get the determinant? So, for example, this is the first minor. You get the determinant. So, we say determinant, you take major diagonal element minus minor diagonal element. So, it's 6 times 2, which is 12. 12 minus 4 times 1. So, 12 minus 4, and you'll get 8. Go to the second one. 2 times 2, which is 4. 4 minus 0. So, 4 minus 0, you get 4. The third one, we have 2 times 4, and you have 8. 8 you minus 0 times 6. So 0 times 6 is 0. So 8 minus 6, you still get 8. Then we come back here. 2 times 3, you get 6. 4 times 9, you get 36. So you are taking 6 minus 36, and you have negative 30. Come here. 4 times 2, you get 8. 8 minus 0. So you still get 8. Here we have 4 times 4, that's 16. 16 minus 0. You have 16. Come here. 3 times 1, that's 3. And then we have 9 times 6, that's 54. So 3 minus 54, you get negative 51. So that one you get negative 51. 4 times 1, that's 4. 4 minus 18, you get negative 14. And lastly, 4 times 6, you get 24. 24 minus 6. 24 minus 6. 24 minus 6, you get 18. You get 18. Good. So you may look at that. We go now to step number 3. Step number 3, after you get the adjoint, now you can get what we call cofactor. And how do we compute the cofactor? How do we get the cofactor? So now let's go back to the adjoint. Go back to the adjoint. Now, how do we get the adjoint? How do we get, after we get the adjoint, how do we get the cofactor? To get the cofactor, use the adjoint. And this is how you get the adjoint. So this is what you do. The first element, you give it a positive. And the other one, negative. Positive, negative. positive, negative, positive, negative, positive. Let me repeat again. We are saying that to get the cofactor, use the adjoint. By allocating the positive sign to the first element, positive, negative, positive, negative, positive, negative, positive, negative, positive. Or you can still do this. Provided the first element you put it a positive, also you can determine to go vertically. Positive, negative, positive, negative, like that. So that's how you get the cofactor. So when you go back there to cofactor, so for example, now this one it is 8. So it's positive 8, so you'll get 8. Then go back here. Here we have negative 4. Here we have, it was positive, but here we have negative. So it will be negative 4. This one will be positive 8. Now, let's go back here. This is negative. So this is negative 30, but here you have a minus. So minus minus becomes a positive. So this one will be 30. Here we have 8. It would be negative 16. This is positive negative, so it will mean to be a negative. So it's negative 51. Negative negative becomes a positive, so it will be 14, which is positive. And lastly 8, which that one will be a positive. Like that. So now let's be here. So that's how we get the cofactor. We have used the adjoint to get the cofactor. Then after that, now we can determine our determinant. Step number 4, you compute determinant. Now this is how we get the determinant. There is 3 ways you can get the determinant. You use the cofactor and the original matrix. Cofactor and the original matrix. So for example, if I want to use the first row, so for example, let's be here. The original matrix, the original row, we had 4, 3, 9. This is what I'll be doing now. I'll be taking 4. You multiply by the first element. So it's 4 times 8. So you can take 4 times 8 plus 3 times negative 4. 3 times negative 4 plus 9 times 8. 9 times 8. Or, I'm saying that to get the determinant, you use the original matrix and the cofactor. Or, you can still do this. It's not a must you have to take the first one. You can also decide to take the second one and the second one. So that means, for example, you take 2, you multiply by 30, plus 6, you multiply by 8, 1, you multiply by negative 16. Or you can still use the third one. So 0 times negative 51 plus 4 times 14 plus 2 times 18. You'll still get the same determinant. So you can use any. You don't use all of the 3. So just use one. And with that, you get 92. This one you get 92. Even that one you get 92. That one you get 92. Even in an exam, actually, you can try to. Because if you get the different figures, that know that you have made a mistake somewhere. Now, after we get the determinant, so our determinant, so in this case, we just select one, which is 92. So how do we get the inverse? So now let's be here. This is how we get the inverse now. Our determinant is 92. You reciprocate. So it will be 1 over 92. And then, note this. You do what we call, you transpose the cofactor. I repeat again. To get the inverse here, after you have your determinant, you reciprocate. And then, to get this element inside the inverse here figure, you just transpose the cofactor. And we say that transposing this where the row becomes the column, and the column becomes the row. So now let's be here. This is our cofactor. We are transposing the cofactor. So the first row becomes the first column. So we'll have 8, negative 4, 8. The second one becomes the second column there. So you'll have 30, 8, negative 16. And the third row becomes the third column. Negative 51, 14, and 18. So that's how you get an inverse of a 3 by 3 matrix. Get a 3 by 3 matrix. So I think we can still try another illustration. can still try another illustration, because an inverse of 3 by 3 matrix is mostly applicable when we are performing what we call Leontief's or output-input analysis. So now, before I wrap this, let me take you back to the steps. We have said that first of all, you get the minor. After you get the minor, you compute the adjoint. After the adjoint, you get the cofactor. After the cofactor, now you get the determinant. From there, now you can get the inverse. So as simple as that. So let's do an illustration. So now let's do another illustration of a 3 by 3 matrix. Assuming now you want to get the inverse. How can we get an inverse of this matrix? So step number 1, you compute the minor. Compute the minor. And this is how we compute the minor. We say that to get the minor, you take first row, first column, first row, first column. Now you take the uncrossed element. So you have 1, 2, 1, 5. 1, 2, 1, 5. First row, second column. First row, second column. So the untouched we have 0, 3 and 2, 5. First row, third column. First row, third column. The untouched number we have is 0, 3, 1, 1. Like that. The other step, you take now the second row, first column. Second row, first column. So we have 2, 1, 1, 5. 2, 1, 1, 5. Second, 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 second. So we'll have 4, 3, 1, 5. 4, 3, 1, 5. And then second row, third column. Second row, third column. We have 4, 2, 3, 1. 4, 2, 3, 1. Now we go to the third row. Third row, first column. Third row, first column. The uncrossed number we have is this. So we have 2, 1, 1, 2. Third row, third row, second column. So we have 4, 0, 1, 2. 4, 0, 1, 2. And lastly, it's third, again it's third. Third, third. So we have 4, 0, 2, 1. 4, 0, 2, 1. That's how you get that. So that's the step number 1. Now let's go to step number 2. Step number 2, you are supposed to get the adjoint. And how do we get the adjoint? We say that to get the adjoint, you compute the determinant of each minor. So for example, in this case, let's go back here. So you take 5 times 1. So you are taking the major diagonal to get the determinant, minus minor diagonal. So you are taking 5 times 1, which is 5, minus 2 times 1, which is 2. So it's 5 minus 2, you will get 3. Here we have 0 minus 6. It will be negative 6. 0 minus 3. You will have negative 3. Here we have 10 minus 1. You will have 9. 20 minus 3. You have 17. 4, you minus 6, you get negative 2. 4, you minus 1, you get 3. 8, you minus 0, you get 8. 4, you minus 0, you get 4. Like that. So that's how you get the adjoint. After you get the adjoint, step number 3, now you can get the cofactor. So how do we get the cofactor? We say that to get the cofactor, you use the adjoint. By the first element, you give it a positive value and the rest negative. So in this case, you can use positive, negative, positive, negative, positive, negative, positive, negative, positive. Or you take the first one as positive, positive, negative, like that. So that means, how do we get our cofactor? So our cofactor will be, this is positive 3. Minus minus becomes a positive, so you have 6. Positive, negative, you have a negative 3. Here we have negative 9. Here we have 17. Here we have minus, so it will be a positive 2. That one will be remain to be 3. This one will be negative 8. And this one will be 4. Like that. That's how we get the cofactor. After we get the cofactor, step number 4, you are supposed to get the determinant. And how do we get the determinant? We say that to get the determinant, you take the original matrix, you multiply by the cofactor. You can just choose any, either the first row, second row, or third row. So that means, for example, let's go back to the original matrix. Under the original matrix, I want to use the first row. So you take 4, so it will be 4. You multiply by 3, plus, here we had 2, so it will be 2. You multiply by 6, plus the last element of the first row was 1. You multiply by negative 3. Or you can still decide to choose the second row, you multiply by the second row. Or the third row and the third row, you still get the same determinant. So here we have 12. Here we have another 12. And then you minus 3. And you'll have a determinant of 21. You have a determinant of 21. And then lastly, how do we get the inverse? How do we get that inverse? So if our determinant is 21, you reciprocate 21, so it would be 1, you divide by 21. And then we say that you transpose the cofactor. The row becomes the column, and the column becomes the row. So that means, for example, in the cofactor, the first row will be our first column in this. So we'll have 3, 6, negative 3, negative 9, 17, 2, 3, negative 8, and then you have 4. Like that. As simple as that. Yeah. So that's how we get the inverse of a 3 by 3. I hope now you're good up to that point. Yeah, for revision purposes, you can develop your own, a 3 by 3, and then you try to compute. How can you know that you are correct? If you want to know you are correct, the determinant will help you. Because if you use the first row, first column, first row, second row, or third row, you should get the same determinant. Good. So I want us to look at another part now. At now we have done addition, subtraction, multiplication, and the inverse. So mostly you need to focus on the last two. That's the multiplication and the inverse. So now let's look at the sum of the application of matrices. So I want us to look at some of the application of matrices and where do you apply matrices in business. One, it's in solving simultaneous equation. Solving simultaneous equations. Number two, demand and supply analysis. Sorry, demand and supply analysis. Number three, also is used in CVP analysis. CVP analysis. Number four, Markov analysis. Markov analysis. And number five, we have what we call Leontief's analysis, or what we call output input analysis. Yeah, those are some of the application of matrices in business. Solving simultaneous equation, demand and supply analysis, CVP analysis, Markov analysis, and Leontief's analysis. So let's start with the first one. In solving simultaneous equations. In solving simultaneous equation. Now, when solving the simultaneous equation, you just develop an equation in terms of y is equals to a plus bx. So from that, now you take the coefficient. In this coefficient, we have a, we have b. Like that. It's as simple as that. So that's how we solve in the simultaneous equation. So I want us to do an illustration on solving simultaneous equation. I'm hoping you have your past paper with you, and we do a question in August 2009. August 2009, question 1A. August 2009, question 1A. I will read. So you can open that question. You have the past papers. For those without the past paper, the good thing is that this question is already included in the handout. So it's advised before the class, be in possession of your past paper, or you have already printed your notes, the notes that we'll share, because some of those questions is already indicated in that handout. It's already there. So let me read. So that means if you don't have the past paper for those questions, the question is already included in that handout for the notes. So, and number one, and that question for August 2009, question 1 said that Utensil Limited is in the production of cups and bowls. The production require machine and labor input as follows. So you are given these. So we are given cups. We are given bowls. So you have machine hours per unit. Machine hours per unit. And then we have labor hours per unit. Labor hours per unit. So for cups we have 4. Here we have 2, 3, 2. Then you are told that the available machine hours and labor hours are 100,000 and 80,000 respectively. So the available machine hours, we have it's 100,000 hours, and labor hours, the available it's 80,000 hours. So that's the information given. Then required, using matrix algebra method, find the optimal number of cups and bowls that should be produced by Utensil Limited. So using the matrix algebra, you determine the number of cups and bowls that should be produced. So now this is the information you have. We have the cups and we have the bowls. For example, this means that for machine hours per unit, that means that we require 4 machine hours to make 1 cup, and we require 2 machine hours to make a bowl. For the labor hours, to make 1 cup, you require 3 labor hours, and to make 1 unit of bowl, you require 2 hours. And then you are told that the available machine hours is 100,000 hours, and labor hours is 80,000. So, how do we solve that? Solution. So, you formulate it. In this case, you just take the coefficients. So, this is what I mean. Based on the information given. So, for example, you start with the machine hours. So, you require 4 machine hours to make a cup, plus 2 hours to make a bowl. That's for the machine hours. And you're told that the total machine hours available is 100,000. That's the machine hours. Now, let's go to the labor hours. You require 3 hours to make a cup, plus 2 hours to make a bowl, and the total number of labor hours we have is 80,000. That's the first step. Then after that, now you can now take the coefficients. So now you take the coefficient. So in this case, I'll take 4, 3, you form now a matrix, 2, 2, like that. So I've taken the coefficients here. And then we have cups and bowls. You multiply by cups and bowls, like that, is equals to, you have this, 100,000 and 80,000. As simple as that. So in this case, we want to determine the number of cups we can produce, the number of bowls. So how do we make it the subject matter? So to get cups and bowls is equals to, now this is what we do. Now let me give you an illustration. If you have 2 times x is equals to 4. This is what you have in here. This one times that one, you get that. So these are known. CB, it's our x. If you have a 2 times x is equals to 4. How can you get x? So to get x, you just divide both sides by 2 by 2. So that one and that one goes. So to get x, so what you have done, you have divided both sides by 2. So that means to get x, now in this case, our x is CB. So to get CB means that you will divide both sides by this matrix. You divide by that matrix, you divide by this matrix. So to get CB, you divide both sides by this matrix, divided by that matrix. So that in this side it will cancel. This one is go to the other side. We say that division is known as the inverse. So it is equals to, you take this one to the other side, 4, 3, 2, 2, but we are saying this one we are dividing. So if you show an inverse, remember you say that inverse is the same as division. And then 100 and 80. Like that. So to get CB, it is equals to, so remember here we have an inverse. We are dividing this. So how do we get an inverse? We say that inverse, we have some steps forward. First of all, you get the determinant. Determinant, you take 4 times 2, which is 8, minus minor diagonal, 3 times 2. So it's 8 minus 6. 8 minus 6, you get 2. And then the other step, you reciprocate. If the determinant is 2, so it will be 1 over 2. You get the reciprocal. And then, we said that when getting the inverse, for the major diagonal element, you interchange. So the 2 goes there, and 4 goes there. But for the minor diagonal element, you change the sign. So that means being positive 2, it will be negative 2. And this being 3, it will be negative 3. So you have get the inverse of that. And then you multiply by 180. So that means our CB, it will be. So how do we get that? Use the rules of 7. That means unachora saba. So first row, first column like that. So you take 2 times 100,000 plus negative 2 times 80,000. So 2 times 100, you get 200,000 minus 160,000. So that one you get 40,000. 40,000 you multiply by a half. 40,000 you multiply by a half. And you will get 20,000. You've not gotten that, get the second one. Now let's go to the balls. You take the second row, you multiply by the column. Second row, you multiply by the column. So I'll take negative 3 times 100,000. That's negative 300,000 plus 4 times 80. That one you get, that's 120. So not 120. That one is 320. So you'll be taking negative 300, you add 320. You get positive 20. And then you get 20,000. Now you multiply by half. And you have 10,000. Like that. So that means cups you should produce 20,000 cups. And balls you should produce 10,000 balls. As simple as that. So let's try another illustration. First of all, look at that one for 10 seconds. And then we do another illustration so that this concept can stick. So that concept can stick. So let's do this question. May 2016, question 1b. May 2016, question 1b. Remember the question. And we are told that a certain audit firm has 2 categories of employees: auditors and assistant auditors. The total monthly salary of 1 auditor and 5 auditors and 5 assistant auditors amount to 456,755. Whereas the total monthly salary of 3 auditors and 9 assistant auditors amount to 985,005 shillings. The firm has a total of 6 auditors and 14 assistant auditors. The employees contribute 12% of their monthly salary toward their circle society. Required: the monthly salary of an auditor and assistant auditor using matrix algebra. So we need to get the average salary of the both auditor and assistant auditor. So in this case, we have the auditor and assistant auditor. So we can do this. So let the auditors be denoted by X, and then the assistant auditors to be denoted by Y. So that means we'll be having X plus Y. X is the auditor, Y is the assistant auditor. Now, how do we formulate that? So just listen to what I'm saying. So let me read again. We are told that a certain audit firm has 2 categories of employees: auditors and assistant auditor. The monthly salary of 1 auditor and 5 assistant auditor amount to that. The salary of one auditor, that's 1x, and 5 assistant auditor, that's 5y. Yeah, the total salary of them is 456. 456, 755. That's what you are given. Whereas the total monthly salary of 3 auditors and 9 assistants, 3 auditors and 9 assistants is equals to how much? Yeah, I told that. Whereas the total monthly salary of 3 auditors and 9 assistant auditors amount to 985, 005. You have that. So, then you're told that the firm has a total of 6 auditors and 14 assistant auditors. So, required number 1, the monthly salary of an auditor and that of an assistant auditor using matrix algebra. So, you already have that equation. So, you formulate it in terms of matrix. So, this one will be, you take the coefficient. So, this will be 1, 3, 5, 9. Then we have xy is equals to 456, 755, 985, 005. To get x and y, it will be equal to, we see that you divide both sides by this matrix. You divide both sides by this matrix, the other side is the same matrix. And we see that if you divide dividing by this matrix, division means the inverse. So that means if you go to the other side, you get the inverse. So it will be 1, 5, 3, 9, but you get the inverse. And then you multiply by this. 456, 755, 985, 005. Like that. Then that means xy will be equal to, so here remember you have an inverse. You use the rules of how are the steps of getting the inverse. So you will take 1 times 9, that's the major diagonal. You're getting the determinant first. 9 times 1 is 9 minus 15. So 9 minus 15, you get 6. Sorry, negative 6. You get negative 6. It's 9 minus 15. You get negative 6. And then you get the reciprocal. So it would be 1. You divide by negative 6. Then, for the major diagonal element, you interchange. So 9 goes up, 1 goes down. But for the minor diagonal, you get, you change the sign. So this one will be, it's positive 5, so it will be negative 5. This is 3, it will be negative 3. And then we have this. We multiply by 456, 755, 985, 005. So what do you get there? X, Y. So this is what you'll do. First row, first column. So you will be taking 9, you multiply by 456, 755, you add negative 5, you multiply by 985, 005. Then what you get, you multiply by 1 divided by negative 6. So in short, what you get there, you divide by negative 6. If you divide by negative 6, you get x, it's 135, 705. To get 4y, you do the same. Now you're using the second row and that column. So it will be negative 3. So you take negative 3. You multiply by 456, 755. You add 1. You multiply by 985, 005. And you get negative 385 to 60. Then you divide by, or you multiply by 1 divided by negative 6. So I just divide directly by negative 6. And I'll get 64 to 10. And you have answered the question. So what was the requirement? You are supposed, number 1, the monthly salary of an auditor and assistant auditor using matrix algebra. So remember our X represented auditor. So that means on a monthly basis, an auditor gets a salary of 135,705, but assistant auditor gets a salary of 64,210. As simple as that. Then part 2 of the question. Let's do part 2 of the question. Now, part 2 of the question, we are told that the employees' total monthly contribution toward their circle. The employees' total monthly contribution toward their circle. So they want the monthly contribution to their circle. Eh? So this is what you do. An auditor gets a salary of 135,705. An assistant gets 64,210. I take you back to the question. We are told that the firm has a total of 6 auditors and 14 assistant auditors. So the firm has 6 auditors, you multiply by 6 auditors, and then they have 14 assistant auditors, so that you can get the total salary. You get the total salary of the auditors and the total salary of the assistant auditor. And then you had been told that the employees contribute 12% of their monthly salary toward their circle. So they contribute 12% of their salary toward their circle. So you multiply by 12%, you multiply by 12%. So that's how you get the total contribution they make per month toward their circle society. And this is 97. So that will be 97, 707.6. Yeah, this is 107, 872.8. So in total, you have 205, 580.4. So that's the amount they contribute to the circle each and every month. Each and every month. Good. So that's the first application of matrices in solving simultaneous equation. So now we can look at the second application. Look at the second application. And the second application is where we use them in demand and supply analysis. So let's go to the second application. And the second application is where we use them in demand and supply analysis. Demand and supply analysis. And I want us to do a question in December 2014. Open that question. December 2014. Question number 1C. Question 1C. Question 1C. I say that those without the past paper, you can use the handout for the notes. The question is already indicated there. But it's advisable, first of all, to have your own past paper. Hoping we are there. December 2014, question 1C. So hoping we are there. And we are told that the demand and the supply function for product A and B is given as follows. So you are given the demand and the supply for the both product A and B. Required. Or let me just write the question here. So the demand and the supply, so you are given products here. We have product A and product B, and then you are given the demand equation. We are told that PA is equals to 1500 minus 4QA minus 3QB. And then for product B, PB, it's 700 minus QA minus 2QB. And then you are given the supply. For the supply, you are told that PA is equals to 400 plus 3QA plus QB. And here you have PB is 200 plus 4QA plus QB. So that's what you are given. You have product A, product B. You are given the demand function, and then you have the supply function. Where we are told that where PA, this PA, is the price of product A in shillings. PB is the price of product B in shillings. QA, we have QA and QB. QA is the quantity demanded for product A, and QB is the quantity demanded for product B. Required. Using matrix algebra, determine the equilibrium prices and quantity for product A and B. So using the matrix to determine the equilibrium, prices, and quantities. So, solution. You see, in this case, they want the equilibrium, prices, and quantity. At equilibrium, remember that demand is equals to supply. So you say that at equilibrium, demand is equals to supply. So let's analyze this. So we start with product A. Product A, remember you said you want the equilibrium prices and quantity. Demand is equals to supply. So for product A, it will take the demand, this is the demand function. We have 1500 minus 4QA minus 3QB should be equal to the supply, which is we have it's 400 plus 3QA plus QB. Then we bring the right terms together. So we have negative 4QA and here we have 3QA. So if you take this one to the other side, it will be negative. So it's negative 4QA minus 3QB. So you have negative 7QA. Negative 3QB, you minus, this one is goes to the other side, becomes a negative. So it's minus 3QB minus QB, you have minus 4QB is equals to, now this 15 you take it to the other side, so it will be negative. So we'll be taking 400 minus 1500 and you'll get negative 1100. So you can correct equation number 1. Now let's go to product B. Product B. So how do we get for product B? You do the same. For product B, demand is equals to supply. So here we have 700 minus QA minus 2QB is equals to 200, that's the supply equation, plus 4QA plus QB. Then we bring the right term together, starting with QA. So you have negative QA minus 4QA. It's negative, this one goes to the other side, becomes a negative. So it's QA minus 4QA, and you get negative 5QA. Then minus 2QB, this one goes to that side, becomes a positive. So it's minus 2QB minus QB, you get minus 3QB is equals to 700, you take it to the other side, becomes a negative. So you'll be having 200 minus 700 and you'll have negative 500. You correct equation number 2. So now, you already have equation 1 and equation number 2. So now, using equation 1 and 2. Using equation 1 and equation 2. But in this case, the examiner is specific. Using matrix algebra. How do you use matrix algebra? So we have equation 1 and we have equation 2. We just take the coefficients. So for example, equation 1, you take the coefficient of QA, which is negative 7, negative 4. Let's go to the equation 2. QA, we have negative 5. Here we have negative 3. Like that. And then remember we had QA, QB. So it will be QA, QB, like that, is equals to, equation 1 was equals to negative 11. And equation 2, for product B, we had negative 500. So now we have that equation. So how do we solve that? So how do we get QA? How do we get QB? So to get QA and QB is equals to, so to get this one, we say that you divide both sides by this matrix. So that means if this goes to the other side as a division, we say that means an inverse. So it will be negative 7, negative 4, negative 5, negative 3, but you divide, so we show an inverse, and then we have negative 11, negative 500, like that. So how do we get that? So in this case, how do we get the inverse? First of all, you get the determinant. So it will be negative 7 times negative 3. Negative becomes a positive. So this is 21. 21. Sorry, is it 21? Yeah, it's 21. You minus is 21. You minus 5 and 4. That's 20. So 21 minus 20 you get. So you are getting, this is 21 minus 20. You get 1. So if you get 1, an inverse of 1 is how much? An inverse of 1. 1 and 1 becomes 1. So it will be 1 over 1. And then, so this one we are looking for QA and QB. So to get QA and QB it will be, so here we're getting the determinant first. So it's negative 7, negative 3. And here we have negative 4. And here you have negative 5. So that's 21 minus 20, you get 1. So it will be 1 over 1. And then we say that for the major diagonal element, we interchange. So this one will be negative 3 goes up, negative 7 goes down. And then for the minor diagonal, you change the sign. So you have negative 4, negative 5. So it automatically becomes positive. So this one will be 4 and this one will be 5. And then you multiply by negative 11. And the other one is negative 500. Like that. So that means our QA and our QB. So in this case, we are looking at the quantity. So what do you get there? What do you get there? What do you get there? So that's 1, 1. And what had we gotten here? So this was negative 7, and that's 4. That one is okay. For quantity B, yeah, so it's okay. So what do we get there? So here we have negative 3. We'll be having negative 3. You multiply by negative 11. Negative becomes a positive. So that means you have 1300, that 300, and we have 4 times that. 4 times that when you get 2000. So 4000 minus, so we'll be having that 300 minus 2000, and you have 1300. Because we are multiplying by 1. And this, the other one, you take 5 times that, and that one times that, so that one will have 55 and 35. So I think the same you'll get 1300. Now, after you get the quantity, lastly, now you can get the price. And how do we get the price? To get the price, you just substitute in the equation, either for the demand or for the supply. Demand of the supply. So I have ignored this. I have ignored this because I have realized I made a mistake here. When I was copying this question, this was supposed to be QA, QB, but I wrote 4QA, QB. So that one will correct, but from the handout, the notes I have given, it's corrected. So in this case, it's only that I made this mistake. Instead of 4, it was supposed to be just QA. So that's why I'll not proceed to that. Yeah. But the process is the same. If you know what you are doing, the process is the same. Nothing changes. So that was the second application. Now, I want us to look at the third one. We look at the third one, and then the fourth and fifth we'll do in our next session. So, and the third application, it's CVP analysis. CVP analysis, we say that matrices is also applicable in CVP analysis. So CVP analysis is just the study of the relationship existing between the cost, profit, the cost, volume, and the profit. And how do we solve that? Remember we said that when you are applying multiplication, for it to be applied, number one, it must be compatible and it must be feasible. Feasible means it's making economical sense. So let's do an illustration on that, which requires application on CVP analysis. So let me read this question. It's not from the past paper. It's from the handout. It's already dedicated in your notes. And let me read the question. It says that the national office of the car rental company, I'll just include the important details here. The national office of the car rental company is planning its maintenance for the next year. The company management is interested in determining the company's need for a particular repair part. The company rents salon car, Subaru, and pickup. So they have 3 types of cars. The matrix N shown below indicates the number of each type of vehicle available for renting in the 4 regions of the country. So you are given now the number of cars there. So I'll indicate the most important. You are given matrix N, which shows the number of salon car. We have Subaru, and we have pickups. Here we have 160, 150, 100, and 120. For Subaru, we have 400, 300, 100, and 400, 500, 200, 150, and 300. You're given like that. And you are given the regions. So this for the coast. Then we have for central. Then we have western. And lastly we have for highlands. So you're given that. So that the matrix N shown below indicates the number of each type of vehicle available for renting in the 4 regions of the country. So that's what you're given. Then you're told that 4 particular parts interested because of their cost and frequency of replacement are fan belts, sparks, plugs, and batteries and tires. On the basis of study of maintenance record in different parts of the country, the management has determined the average number of repair parts needed per car during the year. These are summarized in matrix R below. So those were the cars. Matrix N was for the cars. Those was for the cars. And then we are given for spare parts, given by matrix R. At matrix R, you are given, we have Saron car, we have Subaru, and we have pickups. So here you have 17, 12, 9, 4, 16, 8, 7, 7, 15, 5, 5, 6. And those are the spare parts. So you have fan belts. We have plugs. We have batteries. And then we have tires. We are given that. So required. The total demand for each type of cars. And then number 2, the total number of each repair part required for the fleet. And lastly, if matrix C shown below contains cost per unit in shillings for fan belt, sparks, plug, batteries, and tires, calculate the total cost of all spare parts. So you are given another matrix there, C. This one will represent the cost. It's denoted by matrix C. And you are given it as 1250, 800, 6,500, and 8,000. So now that's the question given. You are given the number of cars and the region. You are given the spare parts for each type of car, and then you are given the cost for the spare parts for fan belts, plugs, batteries, and tires. So required number 1, the total demand of each type of car. So number 1, we get the total demand for each type of car. That's very easy. So number 1, you ask yourself, let's go to the first matrix N. How many types of car do we have? We have 3. We have Saron car, Subaru, and pickup. So you have Saron car, Subaru, and we have pickups. Then you just add the total. They just want the total demand. So for example, Saron car, you add the total for all the regions. For example, coast, they require 160. Central, they require 150. Western, they require 100. And highland, they require 120. You add the total for Saron car. So 160 plus 150 plus 100 plus 120, you get 530. For Subaru, you do the same. You add the total. That is 7, 8. 8, you add that one, you get 1200. So here you have 5, 7, 8. That's 1150. And you are through with number 1. So you can call it, the first matrix, let me call it matrix A. Now, matrix A will show the total demand for all the types of car. Then number 2 of the question. The total number of each repair required. Total repairs required. Now, in number 1, you have gotten the total demand for the cars. And then they want the spares. In matrix number 2, matrix R, you had been given the repair required for each type of car. For example, fan belts, for salon you require 17 in a given year. For plugs, you require that. Now, the question is, you determine the total repair required. So to get the total repair required, it's very easy. You just take the total demand of the cars, of which you are given by matrix A. You multiply by the repair parts required. And our repair part is denoted by matrix R. Let me repeat again. To get the total repair required, you already have the number or the total number of cars. You take the total cars, you multiply by the repairs required per car. So you are multiplied by the 2. But we say that for you to multiply any matrix, it should be number 1, it should be compatible. So for example, you are taking the total number of cars denoted by this matrix. This is A. Can we be able to get the order of A? How do we get the order? We say that you start with the number of columns. By the number of rows, it's 1, 2, 3. So it's a 3 by 1. So it's 1, 2, 3 by 1. You multiply by matrix R. This was matrix R. So who can give me the order of matrix R? The order of matrix R. It's 1, 2, 3, 4. 1, 2, 3. So it's a 4 by 3. 4 by 3. Remember, we say that always you start with the number of rows. So now let's be here. So A, you are taking the total number of cars, you multiply by the total spare parts to get the repair parts, to get the total repairs required. So first of all, for them to be multiplied, you have to test for compatibility. For example, these are 3 by 1 and these are 4 by 3. So we say that you look at this and that to look for compatibility. Is it compatible? This is 1, this is 4. So this means it's not compatible. It's not compatible. So when not compatible, what do we do? So when it's not compatible, you try to interchange the matrices. Interchange the matrices. So for example, in this case, I start with matrix R, which is a 4 by 3. You multiply by A. And matrix A, it's a 3 by 1. So in case they are not compatible, you can try to interchange the matrices. So R, you start with R, you multiply by now by A. Instead of A by 3, A by R, now it will be R by A. So now let's test for compatibility. So here you have 3. We have 3. So is it compatible? So in this case, it's compatible. Because we have 3 and 3. So now let's assume the matrix we have is B. If you take R times A, let's give the product to be B. Can we be able to determine the order of B? Now, if you want to know the order of the product, what you get, you take the first one and the last one. So it will be a 4 by 1 matrix. 4 by 1 matrix, like that. If you want to determine the order of the product after multiplying the two matrices. So now let's compute this. So you see that in this case, you'll start with R because it's compatible already. You start with matrix R. This was matrix R, where we had 17, 12, 9, 4, 16, 8, 7, 7, 15, 5, 5, 6. We have that. You multiply by A. And you already have your A. This was your A, matrix A. You required number 1. We had 530, 1200, and 1150. And it should be a 4 by 1. So how do we get that? First row, first column. So in this case, it will be 17 times 530 plus 16 times 1200 plus 15 times 1150. And the total spare part we'll get here is 45 for 60. 45 for 60. Then you take for the second one. Second column, second row, first column. So it's 12 times 530 plus 8 times 1200 plus 5 times 1200. And you have 21,750. And this one you have 18,920. And this one you have an amount of 17 for 20. Yeah, 17 for 20. Yeah, this is the total spare part required. This was for fan belts. This was for fan belts. This was for plugs. This was for batteries. And this was for tires. Yeah, that's the total spare required in a given particular year. For the fan belts, we require 45 for 60, plugs, like one, batteries, and tires, like that. And lastly, let me read the question. You suppose that if matrix C shown below this is the C, this is the matrix C I had already indicated, contain the cost per unit in shillings for fan belts, spark plugs, batteries, and tires. Calculate the total cost for all repair parts. We calculate the total cost of all repair parts. So in this case, we want to determine the total cost. So in this case, we already here we have gotten the total spare parts required, and then you are given the cost per spare part. So how can we get the total cost? So to get the total cost, you take the total spare parts of which you are given the matrix B. This is our B. We call it matrix B, and our matrix B, the order was 1, 2, 3, 4. It's a 4 by 1. So it's a 4 by 1. You multiply by, after you have the total number of spare parts, you multiply by the cost per spare part. And the cost we are given by this matrix. By this matrix. What's the order of this matrix? So it's 1, and then 1, 2, 3, 4. So it's a 1 by 4. So it's a 1 by 4. 1 by 4. So this is matrix C. So we say that in that case, you test for compatibility. So matrix C, it's a 1 by 4. You ask yourself, is that matrix compatible? Is it compatible? So you are looking at 1 and that, 1 and 1. So it's compatible. That means the answer you get. For example, let's assume the matrix we should get, let's call it D. Who can give me the order of D? So number 1 is compatible. If you want to get the product, if you multiply the two, we have said that to get the product, you take the first one and the last one. It should be a 4 by 4. So it should be a 4 by 4. So we have said that number 1, it's compatible. So we say that it's compatible, but not feasible. Compatible, but not feasible. Let me explain why it's not feasible. So we say that if matrices, when you're multiplying the matrices, and it's used for commercial purposes, it should be both compatible and feasible. And we say that feasible means that it's making economic sense. So this one is not making some economic sense. Why? What is the question? The question the examiner wants, determine the total cost. So if you're told to get the total cost, that means you only get one figure. If you want to get the total cost, you just get one figure. But what you are getting here, our product, which will be 4 by 4, that means you get 4 columns, 4 rows. All those answer. But in this case, we just require total cost. So how do you get the total cost? We should get one figure. So that's why you're saying that, yes, it's compatible, but it's not making any economic sense because we'll get a 4 by 4. That means we get 4 rows, 4 columns. Now, let's try to do something else. What if we interchange? We start with C, and our C is a 1 by 4 times B. B becomes a 4 by 1. So in this case, let's test for compatibility first. We have 4 and 4. So number 1, that our matrix is compatible because we have 4 and 4. And then let's predict our product. Our product D should be how much? Should be what order? So you take 1 by 1. So it will be 1 by 1. So 1 by 1, that means you only get one answer. And that's what was required. You get the total cost. In this case, it will be both compatible and feasible. It's both compatible and feasible. So always start, that means we start with C, and our C, this is our cost here. You'll take this our cost, so which will be 1250, 800, 6500, and 8000, like that. You multiply by B, and our B is what you have gotten here. This we have gotten the total spare parts required. That was our matrix B. So which is 45 for 60, 45 for 60, 21 750, 18 920, and 17 420, like that. And then we get the product. So is that times that. So we'll be taking 1250 times 45 460 plus 800 times 21 750 plus 6500 times 18 920 And lastly, 800 times 17,420. And the answer will be, we have 336,533,000. 533,000. So everything we have done here, you'll get it from the handout, the notes that we'll share later. And that I want to mark that one being the end of the first part of matrices. So we have so far looked at 3 applications. That's solving simultaneous equation, also in demand and supply analysis, and then in CVP analysis. We have 2 remaining applications. That's the Markov analysis and Leontief analysis. So that one we'll cover in our next session. Thank you.